Hello boys and girls, Mr. Pancholi here, and welcome to your first physics lesson. Hope you've all been keeping well, safe, but also hope you've been able to enjoy the sun as well. So we're going to start our physics lessons with Intro to Forces. I think some of you may have already started some of these, so it might be revision. If you have, that's fine. If you haven't, this one's short and sweet, this video. Simply because a lot of the stuff here is quite simple in the beginning, and it forms the foundation, the basis of what you need to learn. There won't be that many exams, well, there won't be any exam style questions in this one, again simply because the exam style questions that are available all make use of information that you'll learn a bit later on in the next videos, so I haven't included them in this one. So this one's just a bit of information to start you off with. It might be shorter than the others, but let's make a start. So by the end of today's lesson, you will know and understand the meaning of, and you'll also be able to give examples of what we call scalar and vector quantities. You'll also be able to understand, and again, give the meaning of, and examples of, contact and non-contact forces. You'll be able to know how vectors are represented, and you'll know the unit of force. So let's start with scalar and vector quantities. When scientists make measurements, and in science we're always making measurements when we do experiments or make observations, the physical quantities, that's the things we can measure, physical quantities that they measure fall into two main categories. We call them scalar quantities and vector quantities. Scalar quantities are those that only have a magnitude, a size. Vector quantities are those that have both a magnitude, which is size, and an associated direction. Now that might not make immediate sense to you, but it'll hopefully be clear in the next few slides. So scalar quantities only have magnitude. They only have an amount or a size. Vector quantities have both the size, magnitude, and the direction. So let's start with scalar quantities. Remember, they tell us only about the magnitude. And examples of quantities that we measure, which are scalars, are things like speed, time, distance, temperature, mass, energy, power, and current. Of course, there are lots more that fit into the scalar list. That's just some of the ones I've listed. You'll notice that none of these measurements tell us anything about the direction of what is being measured. For example, if I say to you the time it took for something to happen, for a reaction to happen, was 30 seconds, that tells you nothing about the direction. Next one is vector quantities. Vector quantities, just a reminder, have both magnitude as well as the direction. And I've listed just four here: velocity, displacement, acceleration, force. Now, you might not be familiar with some of these words. For example, you might not know what displacement is or velocity is. So I'll just let you know. We'll go into a bit more detail on this in the next few lessons. But velocity, I give you the example for scalar, was the time it took for something. In this scenario, in scalar, one of the ones was speed. Now speed might just say that I'm traveling at 30 meters per second. This is scalar, remember, 30 meters per second. Again, tells you nothing about the direction. However, for velocity, I might say to you the direction. For example, 30 meters per second west. So we have two lots of information. We've got the 30 meters per second, that's your quantity, and west is your direction. Direction could also be to the right or up. Displacement means the shortest straight line distance between 2 points. Acceleration means speeding up, or it could be slowing down. But it's the change in your speed over a particular amount of time. And force. Force is a vector because force always has an associated direction. I'll give you an example. An example of force is gravity. Which way does gravity always act? Downwards. There's your direction. And we know gravity also has a size. In this case on Earth, gravity is 9.8 newtons per meter. Newtons per kilogram, sorry. So, in this case, we've got force, and all forces fit into this. It could be weight and gravity, it could be thrust, anything like that. They all have an associated direction. So how do we represent vectors? Remember, vector quantities give us direction. So the best way to do this on a piece of paper is using arrows. Arrows always tell us two pieces of information in science. They tell us the direction. Arrows point towards something or point in a certain direction. And the size of the arrow tells us proportionately how large that quantity is. That's where the magnitude comes in. The larger the arrow, the larger that vector quantity is. And they're usually drawn to scale. So we can compare the size of one to the size of the other. Here's an example. Very simple one. A could be anything. It could be the acceleration being represented, or a force. It could be this velocity. The large arrow tells us that it's a large vector. Now we won't be able to just do that if we just have the one arrow, because it's difficult to compare. What's the scale comparing against? So we have A and B. A is larger, so the vector is a larger quantity. And the vector is pointing to the right. There's your direction. B, on the other hand, is a smaller arrow. So it's a smaller vector. Again, they should be drawn to scale. So however proportionately smaller B is, the arrow, you might use this using a ruler. That's how much proportionally smaller the vector is. The direction is northeast. So again, there's your direction. So I'd like you to pause the video, and in your books or papers, I'd like you to associate the words that are in the boxes with the words that are in the description at the bottom in white with the words that are in the green boxes at the top. Pause the video and take a few moments to do that. Some of these values at the top in the green can be used more than once. So pause the video and have a go at this. Right, you should have got something that looks a bit like this. I've put the associated answer in green below the definition. So as one value increases, the size and the value also increases of the arrow. That's proportional. Scalar would be time, distance, energy. They've got nothing associated with them apart from the size. So the one below it, therefore, must be also a definition for scalar. Physical quantity that has magnitude but no direction. Going down in the red, word for the amount, the size of the quantity. This is mixed up in this one. I apologize for that. This one should be magnitude. And the amount, size, or quantity, again, is a repeat with magnitude. The one in red should say the direction that something, what's used to represent a vector. So the one in the red is incorrect. The actual definition in white is incorrect. A physical quantity that has magnitude and direction is a vector. Therefore, examples of vectors would be acceleration, velocity, and force. See if you got those right. If you got anything wrong, please do change them, correct them. It's not an issue to get things wrong, but always make sure that you correct your mistakes so you have the correct notes in front of you. And a reminder, the box in red has the wrong definition, so you can just ignore that one there. So let's move on to forces. Now we're focusing on the vector quantity of forces. And that's what this whole unit is about. Forces are generally, if you simplify them, they're pushes, pulls, or twists between objects. Forces are always measured in a unit called Newton. So we might say, for example, that if we pull something along the ground, it's being pulled with a force of 3 newtons. And that's represented with a capital N after the number. Forces are grouped into 2 main groups. Contact forces. Objects that we're talking about, so this is the physical objects between which the forces are happening. The objects must be touching for the force to act between them. Non-contact, therefore, common sense tells us that in non-contact, forces can act even when the objects are not touching. And you'll see examples of these two in a second. Pause the video and get this down as your definition in your book, please. Also, at any point, if you have come across any slides that you'd like to take notes for example, the scalar and vector slides, I did forget to mention there to you that if you want to pause the video at any point and make notes, that would be very helpful. So if you'd like to go back at this point to the scalar and vector and make notes on the definitions and examples, that would be helpful for you as well. So go back to those and pause the video and make the notes. Then we'll continue, come back to this slide and we'll continue. Okay, so here are examples of contact and non-contact forces. Remember, contact forces happen when objects are touching. So examples of contact forces are friction. For example, if you rub your hands together, both hands must be touching for friction to happen. Another example is friction between, say, the tire of your bike and the road. The tire and the road must be touching. Then you have a normal reaction force. This is the force that happens when an object pushes back against something. For example, if you put a chair on the floor, the chair doesn't go through the floor because the floor is pushing back with an equal and opposite reaction force. Tension, that happens when a rope or a string or something like that is being pulled. If you leave it floppy, it's not tension. When you pull the rope or the string, it becomes tense, it's tension force. And you have air resistance. And that one you might think that's non-contact, but bear in mind, air is a material. It's made up of air particles. So when, for example, a plane runs through the air, the plane body and the air particles have to be in contact. Air resistance. Non-contact, things don't have to be touching. Gravity. If you hold something up and if you let go of it, it's obviously going to drop. The earth and the thing you're holding up are not touching, yet gravity between them forces it down. Electrostatic force is to do with the force between particles, the opposite poles and charges, negative and positive. And magnetic force is the force felt between two magnets, between the poles of the magnets. When a contact force acts between two objects, the objects experience the same size force in opposite directions. This is Newton's third law of motion, and we'll cover that in more detail when we cover those laws. So at this point, I'd like you to pause the video, copy down these examples, and also the little bit in yellow at the bottom, because that is a fundamental law. It's very important that you know that when objects interact, they always exert forces in opposite directions, but they're always equal. And that concludes our video for today. Hopefully it's been useful, and we'll catch up next video. Thanks again, take care, bye-bye.